Tuesday, we're going to go through some examples. In the discussion session, you guys will get a little bit better with the concept, how these things work. Let's call it mutual inductance, or system with two windings, two sources. Mutual inductance. I'm going to put a simple circuit here. And consider this one for average magnetic circuit, magnetic length. Let's call this one L. And the cross section, I assume, is A. And we don't have a fringing flux. So basically, AG and A, they are the same. Just put it A. So now we have two windings. I want to see what is the inductance in this time. You know what I'm saying? I want to go calculate through the inductance to see what is the inductance. There is a one source here and another source here. So there is a lambda 1 here and there is a lambda 2 here. What I'm saying? So lambda 1 is the N1, Phi1, and lambda 2 N2 phi, right? This is the Phi1, and this is the Phi2, right? In this case, it's a simple case. Phi1 and Phi2, they are the same, right? So basically, Phi1 here is equal to Phi2 is equal to Phi, right? But think about it, if the circuit was like this, just I'm going to put something here. If the circuit was like this, look at here. See, there is a Phi1 here, right? There is a Phi2 here, and these two, they are not the same, right? These two, they are not the same. Over there is simple. Phi1 and Phi2, they are the same. This one you'll see in the homework, you practice it. It's very similar to what I'm doing here in a little bit more of calculation. So basically here, lambda 1 is N1 phi, and lambda 2 is N2 phi, right? Let's draw the magnetic circuit for this one. Equivalent magnetic circuit, So it's gonna. It said as soon as we have the winding, we are gonna put this voltage source, right? So for this one, flux is going this way, positive here, negative here, N1, I1, and the flux will put it this way. So we are going to have a 1 Rm, right? And 1 Rg, right? And here, we're going to have another one. So look at here, it's going like this. N2I2, right? And this is a Phi1 and this is a Phi2. And Phi1 and Phi2, they are the same, they are both phi. So how much is phi in this circuit? Just write a KVL here, right? Minus this one plus this one times our phi plus minus this one. So it's going to be N1 I1 plus N2 I2 over Rm plus Rg, right? Rm plus Rg. Let's replace it in those equation over. Lambda 1 is n1 times this, right? So I'm going to do it this way. n1 square over Rm plus Rg times I1 plus n1, n2 over lambda 2 is equal to right? If you remember, lambda in general was Li, right? Dimension-wise, think about it. It's current times inductance, right? Look at here. Current times something is the material, is in the same type of lambda, right? Let's call this one L11. This is the dimension of this one is L, is a millihenry, right? Henry. And let's call this one L12. I equal to, let's call this one L21. And let's call this one L22. My point is, see, this one, and this one. What is the unit for this one? It's 100, right? Because left side is the lambda is something times I, right? This something has to be 100, right? Dimension-wise has to be 100. So why did I put this one 1, 1? Because this is of this current. We call it self-inductance. This is the winding number 1, right? This is the linkage flux in the winding number 1, right? Linkage flux here has a 2 parts. One part is because of the current I1. One part is because of the current I2, right? Current I1 is the current of this winding. I'm calculating linkage flux for this winding, right? I1 is for this winding. I2 is from the other winding, right? The reason I call this one self-inductance because it's because of its own current, right? This winding, because of its own current, has this kind of inductance. We call it self-inductance. But how about this one? This inductance is because of what? This is this winding, right? The second part of the inductance in this winding is because of that current, right? We call it mutual inductance. This one is called mutual inductance, L12. Again, the same thing here. Inductance in this winding, because of this current, is a mutual. And the second part is the inductance in this winding because of this current, right? It is self-inductance here. There are two self-inductance because we have two windings, right? Winding number 1, winding number 2. And there are two mutual inductances, L12 and L221, right? If the circuit is linear, I mean the materials are linear, all linear, air or even if the magnetic material, still you are not getting to the saturation. If circuit is linear, L12 is equal to L21. You can see it here also. Look at this two. L12 is equal to L22, right? L21, right? Now, I want to tell you another aspect of this one. Can you tell me L11 without writing all this equation? Remember what we calculated for one winding? It was n square over what? R, right? When we did a one winding, we said L is n square over R, right? Can you tell me some, based on this one, how we can calculate L11? Without writing this equation. We wrote all this equation to get to the L11. Self-inductance for this one. See, self. Means, hey, forget this one, right? Get rid of this one. There is not this one, right? If this one is not here, becomes one winding, right? If we have one winding, how much is the inductance? N square divided by resistance of this circuit, right? So this is a very simple circuit. Then let me put a kind of crazy circuit here to see. For example, let's say we have this N1, I1 here. I don't know, there's a resistance here, resistance here, resistance here. Just I'm going to make it as crazy as possible, you know. Something, you know, here, I don't know, here, here. And we have another source here, N2, I2. We have another source here, N3, I3. Right? I want to calculate I could have 100 sources. How much is the L11? If I want to find out L11.
We use that one.
L11. Say, forget this one. And forget this one. Actually, they should have some resistance here. No, it cannot be without resistance, right? Because every leg has a resistance, right? So I get rid of all the sources, right? I make all N2, I2 0. If I make this one 0, a voltage source when it's a 0 means what? Short, right? So how much is the L11 here? N1 to the power of 2. I'll go from these 2 points, find the R equivalent. Like a Thevenin that you had, right?
Yeah.
Go find out how much is the R. So basically the self-inductance is going to be N1 to the power of 2 divided by R equivalent, right? The same thing for L2 too. If you want, go this way, right? You don't have to write this equation. These two quickly you can calculate them, right? These two quickly you can calculate them. This one you have to go a little bit through the equation and those kind of things. So this is a system with the two windings. So we calculated the self-inductance and the mutual inductance. The next part is to calculate what? Energy is stored in the system, right? For one inductor, we knew W is equal to how much? Right? How much is energy here?
Sigma.
Hmm?
Sigma of Li squared.
Or the two systems. Okay?
Plus L
Plus.
1, 2.
I want you to prove this one. I'll do it in the, I'll go through the proof in the Tuesday class in the maybe practice extra hours. But there is another term. Or let's put the complete equation. But these two usually they are equal, and usually we show them with M. Usually we show them with M, mutual inductance. And this one usually we show it with L1. This one usually we show it with L1, and this one usually we show it with L2. If you see this one, L1, L2, and M, if we use this one. So basically, this one is going to be half of L1, I1 to the power of 2 plus half of L2, I2 to the power of 2 plus M, I1, I2. M, I1, I2. So the part is M, I1, I2 is extra. I'll prove it on Tuesday, you know, on the discussion part. Yeah.
In practice, is the mutual inductance usually equal between all windings?
If the materials are linear. If they are not, no, they are not. In this course, we don't deal with the nonlinear material, but at least for this part. But if the material is not linear, L12 and L21, they are not equal. They could be different. But let's assume they are all the time, because there are very, very few cases, they are not equal, So think about this one. How we got this one? Just I want you to practice this one. A little bit think about it before I give you the solution. Remember, how did I get to this equation? I said W is equal to ID lambda, right? That was ID lambda. I got to this one, right? So here, basically, W is going to be I1D lambda 1, something like this. I'm not right. Maybe something like this. Not exactly this one, but something like this. To see, can you get to this equation? Think about this equation, how you don't have to know the proof, but at least do it once to understand. Now, if we have a 3 windings, can you tell me how much is the energy? If you have a 3 windings, it's going to be half of L11 I1 to the power of 2 plus half of L22 I2 to the power of 2 plus half of L33 I3 to the power of 2 plus L12 I1 I2 plus L13 I1 I3 plus L23 I2 I3, right? So the equation we can expand. Usually we don't go to the homework and those kind of things. But I want you guys to know, if you have hundreds of them, also the same equation applies. You know what I'm saying? You can go through the same equation and same thing. So just to summarize here, see, I'm going to write this one like this. Lambda 1, lambda 2, is like this. If you have a 3 windings, I'm going to write it. If you have a 3 windings, I'm going to write it here. Just if you have a 3 windings, it's going to be lambda 1, lambda 2, lambda 3, L11, L12, L13. I'm not sure. L13 side. L21, L22, L23, L31, L32, L33. My point is, doesn't matter how many windings you have. That's the same equation. And usually, these two, they are the same. This one and this one, they are the same. This one and this one, they are the same also. There are 3 mutual inductances here, right? Because we have a 3 winding between 1 and 2, 1 and 3, and 2 and 3, right? This is just kind of, if you have more than 1 winding, you guys, how you should, treat this. That equation for the energy, think about that, and we'll go over it, in the discussion session. So you can take down this one. Now, I think this is the end of chapter 1, I believe. Oh, there is one more thing in chapter 1. I'm going to think about it a little bit to see if do we want to cover it or not. There is a hysteresis loss and those kind of things also. We covered it already in the power system. For those ones they didn't have it, go check those notes from the power system. But there is about the hysteresis loss and eddy current loss. It was all covered in the power system, of course. There is one more thing. Maybe I'll cover that one. I'm going to think about it a little bit to see. Let me think over over the weekend to see. Oh, not weekend, until the class, to see. Maybe that's a magnet, permanent magnets. What all I'm saying here is like an air gap core, I don't know, iron core, number of the windings,